One of the nicest type of series is the so-called telescoping type of series. And there's not a real good strict definition for what makes a series a telescoping series, except that its partial sum sequence allows for canceling, and I'll show you what that means. For nice canceling, and whenever a mathematician throws out words like nice, it means that it's, you know, not a really great strict definition, but it should be pretty intuitive what's going on. And so here's an example. We're going to show that this particular series converges to 1 by evaluating the limit of its partial sum sequence. All right, so what do we need to do here? We need to, we'll start by labeling a few things. So remember, a series is an infinite sum, and we're going to add up these we'll call them ANs because that's our index is variable is n. So that means that our AN is equal to 1 over n minus 1 over n plus 1. But a series is about adding up a bunch of these. So let's talk about the partial sum sequence Sn. Okay, well Sn is going to be A0 plus A1 plus dot 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 plus, let's do AN minus 1 plus AN. Okay, and so we'll use this formula. I know often I start at indexing at 0, but in this problem we can't because, well, 1 over 0 doesn't make any sense. So in this problem we have to start, as the series tells us to, index at 1. So there's A1, there's A2. Those will be the first two terms in this particular series. All right, anyway, A1 is going to be, and let's put them in parentheses, 1 over 1 minus 1 over 2. A2 will be 1 over 2, replace all the n's with 2's, minus 1 over 2 plus 1 is 3. AN minus 1, AN minus 1 minus AN minus 1 plus 1, which of course is AN. And finally, AN is going to be just 1 over n minus 1 over n plus 1. And this is a telescoping series, and what makes a telescoping series telescoping, as I said, is that the partial sum sequence Sn allows for nice canceling. And you can kind of see how in the partial sums, negative 2 cancels with positive, negative 1/2 cancels with positive 1/2. And if we were to write another term, if we were to write this A3 here, 1/3 minus 1/4, this negative 1/3 would cancel with that positive 1/3. The negative 1/4 would cancel with the 1/4 and the dot dot dots. Likewise, going from the right, the positive 1 over n cancels with the negative 1 over n here. This positive n minus 1 would have a negative n minus 1 back here. And as it turns out, we are lucky enough to get that the partial sum sequence Sn, what is left? Everything canceled except for the leftmost and the rightmost terms. 1 over 1 is 1 minus 1 over n plus 1. So that's my Sn right there. That's my partial sum sequence. So if I want to know what the infinite sum is, if I want to know what the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1, I could write that as an infinite sum. That's 1 over 1 minus 1/2 plus 1/2 minus 1/3, 1/3 minus 1/4. What that ends up being is the limit as n goes to infinity of Sn. The limit as n goes to infinity of 1 minus 1 over n plus 1. And we know from calculus 1, because sequence limits can be computed like function limits, 1 over something going to infinity, that limits to 0. We can split this up amongst the difference. 1 minus 0 is 0. So if we ever find that a series is equal to 1, because it's equal to the limit, and that limit converges, then we say the series converges. And in fact, it converges to 1 in this example. All right, let's take a look at another. we're given this series here. We want to know if it converges or diverges, and we'll actually, if we don't care what it converges to, we'll learn about nicer methods of determining this in later. But for now, we can actually use telescoping series. This is actually very secretly a telescoping series, and let me show you why. If we take, if we call this, we'll call this AN again, and we take AN 2 over, and we can factor the bottom here, right? That's n plus 1 times n plus 2. And we could actually use partial fraction decomposition on that to simplify things a little bit. And I'll go ahead and spoil the fun for you. You do all that work like we did when we were trying to integrate functions like this. The end result is we're going to get 2 over n plus 1 minus 2 over n plus 2, and you can check my work on that. In fact, it's easier if you just to check this, because you can actually get a common denominator. That's 2n plus 4 minus 2n plus 2, and you can see how 4 minus 2 is 2. All right. So once we're here, we can find the partial sum sequence Sn. That would be a0, and we do start at 0 in this case because of up here, n equals 0 is where we start. a0 plus a1 dot 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 an. That's going to be, let's find out, a0 will be 2 over 0 plus 1 minus 2 over 0 plus 2, plus a1 would be 2 over 1 plus 1 minus 2 over 1 plus 2, dot dot dot. The final one, an, is going to be just the formula, 2 over n plus 1 minus 2 over n plus 2. And just like before, we see that we have things that cancel. This is negative 2 over 2. This is positive 2 over 2. So we'll cancel those. This would cancel with something in the dot dot dots. This would cancel with something in the dot dot dots. Because it's telescoping, we're left with just the first and the last. 2 minus 2 over n plus 2. That tells me that the series 2 over n squared plus 3n plus 2, n equals 0 to infinity, is the limit of the SNs, which we computed to be 2 minus 2 over n plus 2. And sure enough, that's 2 minus 2 over something going to infinity is 0, 2. It converges, and we actually know it converges exactly to the number 2.